So the question is, how do we find the axial torque resultant? We follow the same approach that we followed with axial loading. So the axial torque resultant is T, and in general, in a shaft, can be a function of where you are along the shaft. So now we introduce an x-axis. So let's take our good old wall, and now we put a shaft like that, and we put an axis x. Now the way that the shaft is going to be loaded in torsion is not through forces, but through concentrated torques. So the way the loading is going to look like is going to be something like this. I'm going to tell you there is a torque Q at this end, and maybe there is going to be another torque W at this spot here. We don't see any forces in this simple treatment of torsion in 201. I've already done the digestion of telling you there is a torque there. Of course, those torques do not come out from thin air. Somebody's doing something on the shaft. So if this is your shaft, in order to make the torsion, somebody must have stuck a bar in there, something like that. And if the thing is like that, it must be pulling like that and pushing this way, twisting the bar there. You see that? So I do not even give you this picture in these problems, because these forces will be coming out and into the board. I cannot draw in and out of the board. I am good at drawing, but man, I cannot draw in 3D. Okay, so I'm not going to show you these forces coming in and out. I'm going to show you what this force couple does. And what this force couple does when I stuck a stick into my shaft and done that is I give it a concentrated torque there. You see? I can get the same way if I put like a gear around here. That's a very ugly gear. But if I put a gear around the end of the shaft, and maybe this thing is connected to another gear here, I can have the shaft being rotated by another gear and give a torque. All this is hidden from you. All what I give you is, forget about this. All what I give you is concentrated torques for now. We're going to do distributed on Thursday. But for now, concentrated torque. You look at this and you say, I'm not even going to deal with these rotating things. I'm going to transform them into double arrows. There it is. This thing is going this way. Which one is the axis? Left? Exactly, that way. So I'm just going to draw it like that. Double arrow Q. This guy, which way is going? There or behind me? Behind me. I draw it like that. And now look how similar this thing looks to what we know how to do so well in axial loading. It's just that it's a double arrow instead of a single arrow, right? So what do we do in axial loading now? We do sum of the forces x equals 0 to find the internal force resultant. So we would cut here, boom, 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 if it was a force, expose the axial force, and find it by equilibrium. We do exactly the same way in torsion, right? So the idea is exactly the same. If I want to know what is the torque inside this shaft, I cut it so that now I have only this little stub. Out of this comes Q. And what comes out of this guy? To balance it. Who is coming out? Big T. My axial torque resultant is coming down. And whoops, I have to draw it with the head like that. And if I cut at x, what comes out here is T of x, torque of x. Not out, torque comes out. It's the resultant that comes out. The same way in axial loading, N was coming out. Right? This is Q. OK, now I need to put it in equilibrium. Do we do sum of the forces x? There are no forces. The forces are gone. All what we have is torques. The axial loading was may the force be with you. The torsion is may the torque be with you, like Darth Vader, right? Okay, so the force is gone, the torque is in. We don't do forces anymore. We do sum of the moment x equals 0. So we need to project the moment along the x-axis. Now notice that I do not even bother to put a pivot point here. Even if I told you always moments, you have to give me a pivot. The reason I don't give you the pivot is because all the moments are concentrated moments. There is no forces for which I need to calculate a pivot point to get the moment. Okay, so don't even bother with the pivot for torsion. Sum of the moments along the x-axis must be 0. So let's project this along the x-axis. Is Q coming out positive or negative? You guys are like way ahead of me. Is T of x going to come out positive or negative? Negative, because when I project it along x, it goes the opposite way. Minus T of x equal to 0. Well, look at that. T of x is equal to Q. I found T of x. And this is true for any place I cut between this spot and this spot. If now I cut at a different x, say I cut here, past the point where W is applied, and I get this whole shaft up to here so that I see Q and I see here W, where I cut, I still expose T of x. Always come out. Remember, always out. If I was cutting and looking at the other side, it would come out the other way. So now this is Q, this is W. Again, I do sum of the moment x equal to 0 is equal to Q, positive. How about W, positive or negative? Negative. I love you guys. Q, W, and T of x? Negative. And there we go. We find T of x is equal to Q minus W on this side. Absolutely beautiful. Guess what I do now? I do an axial torque diagram. T of x. Boom. X. I come up here. I get Q all the way up to when I hit W. I go down by W. In this area here, I'm going to have Q. In this area here, I'm going to have Q minus W. And my axial torque diagram is done. Okay? So for this segment between here and here, I'm going to have this constant torque, Q. How do I find the angle of twist for this segment? I use my equation in which at the place of T, the axial torque resultant, I put Q. And I find the angle of twist from here to here. If I want the angle of twist from here to here, I substitute Q minus W for my torque. I find the angle of twist from here to here. What is my total angle of twist? Do I need to worry about figuring out, which way? I just sum it up. The same way as I tell you, the elongation from here to here is 2 centimeters. The elongation from here to here is 2 centimeters. I sum them up, I get the total elongation. If one is negative, it subtracts. I just sum it. So my angle of twist is going to be maybe, 5 degrees from here to here, 2 degrees from here to here. I sum it up, I get 7 degrees of twist. Remember to do this in radians. Right? So I should say pi over 35, pi over 17. Sum it up, I get the total angle of twist. Okay? As simple as that. Actually, now, if you want, you could even do like statical indeterminate torsion, right? No problem. Same ideas. Now, the only thing we didn't talk about yet is what is the reaction at the supports, right? I tell you the internal torque resultant, but what happens at the supports? So what happens at the supports is very simple. The supports do what they need to do to keep the bar in equilibrium. So if this is your bar, and you have a torque Q here, and you have a torque W here, how do you find what happens at the support? Take away the wall goes, and you substitute the wall with the reaction at the support. So the reaction at the support is the Cartesian component of the moment at the support along the x direction. That's the only thing you need to keep the bar in equilibrium. How do we draw Cartesian component? Do we care if it twists this way, or do we look at the axis? Axis. So at the support, I draw the reaction at the support. So if this is point A, I'm going to draw, if this is the x direction, I'm going to draw this thing as mxa. This is my x component of the reaction moment at point A.
So is this the same diagram as that one?
This one here is I cut. So this one is not the torque. So I took away, I did not cut inside the bar. To do the diagram, what I did is I went here and I said, I need the reaction at this wall. Boom, goes away. I don't want the wall anymore because I want to know what it was doing. So instead of the wall, I substitute the wall with what the wall was giving me, which was a concentrated torque to keep this bar from spinning like crazy, right? And I write it as mxa positive with x. And then to find it, I just do the same thing. I do sum of the moment in x equals 0, and that's equal to mxa plus q minus w, from which I find that mxa is equal to w minus q. Okay? And if I had q bigger than w, like I drew it over here, because you see when I did the axial, I see you, so I'll get you in a second. If I did it over here, so I made q bigger than w, that it means that my axial torque at the support, the reaction torque, will be pointing to me. Okay? Yes? I answered. Okay. All right? So now you actually would know how to solve any problems in which you just have concentrated torques, right? Can do statically indeterminate the same way. Get rid of the support, put the redundant torque at the support, put everything in equilibrium as if that was a torque, and then impose what if you wanted to do a statically indeterminate problem? If I have a bar between 2 volts, like that, with a torque in the middle, I'm twisting it this way, and the wall stop here and stop here, what must be true? The total phi is 0. The same way as for a bar between 2 walls, the total elongation is 0. Or in other words, the displacement at the end is 0. Or in this way, the rotation is 0, right? That would be my compatibility constraint. You guys are awesome. And I have to stop because we are done. Thank God for the end of the hour. Otherwise, I'd just keep going, right? OK. So we're ready for Thursday. Do your quick homework on stress and strain. You're good. All right, thanks.
We had a great